Hello everyone, welcome to the course on magnetism in condensed matter physics. Today we will be going to talk about adiabatic demagnetization. This is a technique which can be used to cool samples to a very low temperatures. Here we will use some ideas which we have developed it while talking about paramagnetic materials. And this topic will bring out the idea of entropy rather clearly. Consider a sample of paramagnetic salt which contains n independent magnetic moments pointing randomly. So without a magnetic field applied, the magnetic moments will point in random directions. Since these are paramagnetic materials, so the moments here will not interact with themselves and the system will have no net magnetization. Now suppose a magnetic field is given along the x direction, then the majority of magnetic moments will try to align in the field direction to produce a net magnetization. But in case of paramagnetic materials, there is an effect of temperature also, as an increase in temperature T will again disalign these magnetic moments. So therefore, the magnetization will reduce and at some point it will again reach zero. So therefore, the magnetization will depend on the ratio of magnetic field to the temperature. And as you increase magnetic field, the magnetization will increase, and if you decrease temperature, then also the magnetization will increase. So therefore, this magnetization will be maximum if the magnetic field is high and the temperature is low, and the magnetization will be minimum or zero if magnetic field is low or the temperature is very high. So therefore, there is always a competition between thermal energy and magnetic energy. In the first case, the magnetic energy will be larger than the thermal energy, while in the second case, the magnetic energy will be low compared to the thermal energy. So therefore, at high temperatures, the thermal energy term kVT is so large that all states are equally populated, irrespective of whether or not the states are energetically favorable. In this paramagnetic system, the amount of order can be described by the entropy as in the state of randomness, the entropy will be large, while when there is net magnetization, the entropy will be low. Now in the previous video we have derived the partition function for any general value of j quantum number as sine hyperbolic 2j plus 1 x by 2 divided by sine hyperbolic of x by 2, where x was given by gj mu bb divided by kbt, or in terms of beta we can write gj mu bb times beta, where beta is 1 divided by kbt. Also the entropy of the system is given by U minus F divided by T, where U is the internal energy and is given by minus 1 divided by Z times del Z by del beta, and we can write this in the form of X as 1 divided by Z, then del Z by del X times del X by del beta. And from this relation we can calculate del X by del beta as Gj mu bb. So therefore, the internal energy will be given by 1 divided by z and then the partial derivative of z with respect to x times gj mu bb. So if you differentiate the partition function with respect to x, you will get, and if you simplify this by substituting the value of z also, then you will get u as this. Let's call this equation 1. Now also the Helmholtz free energy F is given by minus kVt times ln of z, which will be equal to minus kVt ln sine hyperbolic of 2j plus 1 x by 2 divided by sine hyperbolic of x by 2. Let's call this equation 2. So therefore, using 1 and 2, we can calculate the entropy as, let's call this equation 3. And it is very important to know the consequence of this equation. For that, let's plot this entropy as a function of temperature for J equal to half. Now I have plotted this equation 3 using Python for different values of magnetic field B. The curve of entropy as a function of temperature looks like this. Now here let's consider the limiting cases for temperature tending to 0 Kelvin or at very low temperatures, and the magnetic field value is approaching to 0. So in that case, the entropy will be some finite value, which will be low because the temperature is low, but as the magnetic field is 0, so the moments will not get any particular direction of alignment. So therefore, still they will be randomly oriented. But if we increase the magnetic field, then the moments will find a direction of alignment. So in that case, the entropy will tend to 0. That you can see in this graph by this particular range. As this blue curve is representing B is equal to 0, and if you increasing the magnetic field, then the entropy curve is going down and down to reach the value as 0 for higher magnetic field. So therefore we can conclude that the application of magnetic field reduces the entropy at constant temperature. Now let's see when the magnetic field is some constant value B naught, and let's say in this graph it is somewhat about 1 Tesla. Now let's see what is the effect of temperature. So here you can see as temperature is close to 0 and there is some finite magnetic field, then the entropy is 0 as the magnetic moments find a direction of alignment. But as you increase the temperature, the entropy is increasing. This is because these moments are randomizing, and at higher temperatures, the system is completely disordered. So therefore, an increase in temperature will cause an increase in entropy at a constant field. Now these two cases are very important in understanding the adiabatic demagnetization. Now let us see how these two cases can give rise to the cooling of a sample. Now let's see the cooling via adiabatic demagnetization. So to understand cooling via adiabatic demagnetization, let's revise two important processes in thermodynamics. So the first process is adiabatic process. So adiabatic process corresponds to when there is no exchange of heat between system and the surrounding. So therefore dq will be equal to 0. And as we know that dq is given by TdS, so this will be equal to 0, and at a finite temperature the change in entropy has to be 0. Here you must note that this entropy is the entropy of the system. Now the second process is isothermal process where the temperature is kept constant. So therefore the change in internal energy, which is given by Cv dt, will be 0. So therefore internal energy is constant for isothermal process. Now you need to remember another important concept, that the magnetization will reduce the entropy while the demagnetization will increase the entropy of the magnetic moments. Here you must note that it is the entropy of magnetic moment which will be increased or decreased by the application of magnetic field. The principle of magnetically cooling a sample follows two major steps. The first step is isothermal magnetization, where we apply a magnetic field at a constant temperature. Now, few minutes back, we have seen that it will reduce the entropy, so that an application of magnetic field from B is equal to 0 to B is equal to 4 Tesla will reduce the entropy at a constant temperature. For example, here this temperature initial is 2 Kelvin. Now the second step is the adiabatic demagnetization. Here you isolate the sample thermally and reduce the magnetic field slowly, so that the process is quasi-static and the entropy is constant. Here again the entropy is the entropy of the system, and the system contains the lattice as well as the magnetic spins. And here in this plot, the entropy is corresponding to the entropy of the system, where I have included the T cube term from the lattice vibrations also. Now as you are demagnetizing the sample, the entropy of spins will increase in a way to keep the entropy of the system constant. So therefore, the entropy of the lattice must be decreased, so that if the lattice entropy is decreased, the temperature of the lattice will automatically decrease, and therefore we reach a lower temperature that you can see from this B to C path. As this process B to C is adiabatic, the entropy here is a constant, therefore the temperature reduces from 2 Kelvin to almost of the order of millikelvins. So therefore during the adiabatic demagnetization, the entropy of the sample remains constant, but the entropy of the magnetic moments increases, which is precisely balanced by the entropy of the phonons, which decreases as the sample cools. So therefore the entropy is exchanged between phonons and spin. Now let's see the schematic diagram for the experimental setup. Here you can see the schematic for the experimental setup for magnetically cooling a sample. Here the sample is placed in contact with liquid helium, which has the temperature of about 4.2 Kelvin, and the liquid helium is surrounded by a jacket of liquid nitrogen, which has a temperature of 77 Kelvin. This acts as a cost-effective thermal shield as it absorbs environmental heat, thus significantly reducing the boil-off rate of the much colder and much expensive liquid helium, ensuring it remains liquefied for longer periods. The liquid helium chamber is connected to a vacuum pump or the liquid helium supply, so therefore when needed we can fill the helium in or we can remove helium using the vacuum pump. And similarly the liquid nitrogen is also connected to a vacuum pump or to the liquid nitrogen supply. The liquid helium and liquid nitrogen are placed in a fiber reinforced glass FRG. This fiber reinforced glass has zero thermal expansion. The sample is placed in a strong magnetic field produced by these strong magnets. So now let's see what is the process to magnetically cool the sample. So in this step 1, the magnetic field is 0, so that the entropy is high. Then you fill this chamber 1 with liquid nitrogen, and then you fill this chamber 2 with liquid helium. so that the initial temperature of the sample will reach up to 4.2 Kelvin. Now as the sample is placed in the bath of liquid helium, so the temperature will remain constant. So therefore, you can apply magnetic field so that this process will become isothermal magnetization. So this magnetization will reduce the entropy so that in the graph you will go from A to B at a constant temperature Ti equal to 4.2 Kelvin. Now at the magnetic field B, at B you have some low entropy and the initial temperature is 4.2 Kelvin. Now in the second step you will remove the liquid helium and liquid nitrogen with vacuum so that the sample is isolated from the helium bath. Now reduce the magnetic field slowly to reach zero. Now as the sample is isolated from surrounding, this process will be adiabatic demagnetization, for which the entropy will be constant. And this entropy is a combination of lattice entropy and the spin entropy. Now as the spin entropy increases because of the demagnetization, the lattice entropy decreases, because of which the temperature of the sample will decrease. Now using the graph of entropy as a function of temperature, let's see this cooling process. So here you can see that the initial temperature is 4.2 Kelvin. So we are at the point A, and which corresponds to the random spins at higher temperature and low field, which is in the blue curve. So this magnetic field value is very low. So here you can see the arrangement of spins is random. Now at the same temperature 4.2, we will magnetize the sample from magnetic field 0.01 to about 4. So the system will reach at point B, where most of the spins are aligned in the field direction. So this process is known as isothermal magnetization. And now the system is reached at point B. Then you will thermally isolate the sample and remove the magnetic field slowly so that the total entropy is constant, but the entropy of the spins will decrease, so they again will orient in random directions. And since here I have assumed that j equal to half, so there are only two possibilities of up and down, so that this final temperature, as you can see here, is about 4 Kelvin, but that is not very close to absolute zero. So therefore we will repeat this particular process again, but this time we will start from temperature 4.0. So this time this point A will shift to a lower temperature for 4.0, which was assumed by the previous process. Now again at this constant temperature we will magnetize the sample so that it reaches to a point B and then again to a point C. Now this point C is now corresponding to 3.8, so that we will repeat this process of isothermal magnetization followed by adiabatic demagnetization again to reach a lower value. And this process is repeated till we reach to a point which is very close to absolute zero. Now there is a very big question, that this method of cooling, does it have a limit? At the first sight it looks like for B is equal to 0, the entropy can reach all the way up to 0. Thus the adiabatic demagnetization looks like it might work as a cooling method all the way to absolute zero. However, in real systems, there is always some small residual internal field, which ensures that the entropy falls prematurely towards zero when the temperature is a little above absolute zero. Thus, the size of this residual field puts a limit on the lowest temperature to which the salt can be cooled at. In certain salts, which have a very small residual internal fields, The temperature of a few millikelvin can be achieved. Now let's see the advantages and disadvantages of this method. The first advantage is it is very efficient cooling technique as it can achieve temperature close to 10 millikelvin. Also, it is relatively simple to implement as it doesn't require any complex equipments or materials. Lastly, it is a non-destructive technique so it doesn't damage the material being cooled. While the disadvantage is it is very slow cooling technique as it can take several hours or even days to cool a material to a very low temperature. Secondly, it is not suitable for all materials and it can be used to cool materials that are magnetic. Also, it is very expensive to implement as it requires use of strong magnets and liquid helium. But nevertheless, adiabatic demagnetization is a powerful cooling technique that has a variety of applications. It is a very efficient, simple, and non-destructive technique, but it is also very slow, not suitable for all materials, and can be expensive to implement. So, this is it for today, and in the next video, we will start a new chapter which will consider the effect of environment around the magnetic moment. There, we will also talk about magnetic resonance techniques. So, stay tuned, and we will meet next time. Thank you so much for watching this video.